Today we are going to study the force method for frames. Actually, the method is quite similar to the one that we applied for the case of beams. For example, in the same way we have to write the compatibility equation and then find the deflections and then substitute the values and we will get the reactions. But the force method is suitable for single story. For example, if this is the frame, this is like a single story frame. For these type of frame, this method works quite well. But in the case when there is a multi-story or multi-way frame, for example, if a frame is like this one, then this method gets quite complicated because because there are more calculations that are required to be performed for these kind of frames. So usually for such frame, this slope deflection method or other method works well, which we will be discussing in the next classes. So for now, we will be focusing on this force method, and there is not much numerical derivation or any other thing. So we will start with the numerical problem directly. It is quite similar to the one with the beams, and after solving one question, you will get the idea. There are a lot of calculations involved, so I expect everyone to have the calculators with them. I'll be asking the questions from you, so be attentive and do make your own notes.
तो ये कौन सा मेथड पढ़ेंगे? ये कौन सा मेथड हम पढ़ेंगे?
I can't hear you properly. Can you speak again?
मैंने कहा हम जो लास्ट टाइम हमने फोर्स मेथड पढ़ा था ना, इस दफा हम कौन सा मेथड पढ़ेंगे?
We are still doing the force method, but now we are doing it for frames. Okay. So we have this frame. So what is the degree of indeterminacy of this frame?
Sir, 4. Yeah, 3.
How much? Degree of
4, yeah, 3.
4 or 3? How?
Sir, हमारे पास 4 unknowns है और 1 known है.
4 unknowns. How many equations we have?
2 sir, तो 2 हो जाएगा.
2 equations or 3 equations? In the case of beams, usually we have 2 equations because there is no third one. But in the case of frames and trusses, you should always consider 3 equations.
हाँ, sorry, moments के लिए. ठीक है sir.
So the degree of indeterminacy is 1. So if we can remove one reaction, we can make this beam make this frame as a determinate beam. So let's call this, just like in the case of beam, let's call this one as a primary structure, and this one as actual structure, and the primary structure. Let's consider that we remove the horizontal reaction from this particular support or at a support. So we will have a roller support over here and a hinge support at this end. There is this reaction of 40 kilonewton per meter. And in the third case, we will assume that, or we will apply this particular reaction that we have removed, and again note down the deflection. So this reaction is this one. As a result of this reaction, this frame will deflect inward, and we have this deflection. Let's call this as delta dash A, A, and we'll remove all other forces. Now in the case of frames, it's usually difficult to figure out the exact shapes of elastic curve. So for the frames, or even in the case of beams, you can apply this methodology. For the case of frames, you can assume the deflection in the original frame. For example, in this one, you can guess because there is no any other load. So when you will apply the force in this direction, obviously the frame is going to deflect towards right. So you will assume that the original frame will also deflect in this direction. For example, we will say that this member is going to deflect in this particular direction. But just keep one thing in mind, that in the case of beam, we would usually neglect the signs with the deflection. For example, if deflection was minus PL cube over 3 EI, we would use the absolute value. But now, since you are not using the exact direction, you are using the same direction for both in the primary structure and in the case when the redundant load is applied. So you will also assume the sign, and later you will see that if you get the negative sign, your assumed direction was incorrect and it is in the opposite direction. And if you get the positive sign, your direction or your assumed direction was correct. So you just someone's mic is turned off. Can you please turn it off? Daniel. So
सर redundant structure में तो roller support है ना, तो like हम AX क्यों ले रहे हैं इसमें?
because
Sir,
we have removed the which reaction we have removed in this original structure, the horizontal reaction, right? Who is this? May I ask you to please turn off your mic? So we have removed the horizontal reaction in this one. So in the redundant, so we are basically applying the principle of superposition. So in this beam, we have again applied this horizontal reaction, and the sum of these two frames would be equal to this one. So the reaction which we remove in the primary structure, we would apply that particular reaction in the redundant structure. Is it clear?
Right.
सर ये यूटीएल कहाँ पे लग रहा है?
Over here, in this frame, if you see that the UDL is acting at 10 meter, this left distance is 5 meter and right distance is 5 meter. The original beam is given in the slides. I have already uploaded this. This is the question. So the direction is clear. Now,
सर ये स्ट्रक्चर में हम सारी डिफ्लेक्शन नहीं शो कर रहे हैं, जो यूटीएल की भी डिफ्लेक्शन है.
it's up to you, but we don't need it because we only have one particular one unknown that we need to find out. So we will show only that deflection. We only need to find out this AX. If we were supposed to calculate some other reaction, then we would have shown the whole shape. It will deflect something like this, right? So what will be the compatibility equation for this frame? Daniel, what will be the compatibility equation? Harun,
So delta A plus delta dash AA is equal to 0.
plus delta dash AA. Okay, in today's question, there will be multiple things. I will be asking everyone one by one, and those who will be giving me answer, I will mark them present in today's class. And we will continue this practice in next 2 or 3 classes. There will be calculations about deflection, about integrals. So be attentive, you know how to do these, and I will be asking you one by one. So first one was Harun. Okay, so we have the deflection, and if I simplify this one again, this delta dash AA would be equal to FAA, that is the flexibility, and this reaction as AX. So 0 is equal to delta A plus FAA into AX, right? So in the case of beam, we can figure out these deflections directly because we have some direct formulations available, but this is not the case in frames or trusses because every frame or truss have different kind of loads that are acting or different support conditions. So we need to figure out these directly by using some method. So we are going to do this. I'll be using method of virtual work in most of the cases. So you can apply some other method if you feel convenient. So it's not compulsory to use this method. So for virtual work method, you remember that the equation for the deflection is 0 to L, capital M. And if I revise this one, this capital M is the moments that are acting on the frame when all the external loads are acting. And this small m is the moment or the equation of moments for the frame when the virtual load of one is acting in the direction of desired displacement. For example, in this frame, if I want, for example, this is our primary structure, and for this frame, I want to figure out this deflection delta A. So capital M would be the one would be the moment equation when these external load that 40 kilonewton per meter is acting on this frame, and I will write the moment of equation for the whole frame. And small m will be the equation of movement for this frame when I remove this 40 kilonewton and apply a unit load of 1 at this in this direction. Why this direction? Because I want the horizontal deflection for this particular frame. So let's write the equation for capital M. I will plot the frame over here again. So how many sections do we need to take in this frame? This is 40, 10, 5, 5, 5. So how many sections do we need? Abbas.
6 sir.
How many sections?
6 हर सेक्शन हर बीम को सर 2 दफा डिवाइड हाफ में वो कर दें डिवाइड.
Why 2 times?
नहीं सर.
Sir, 5 times, sir.
5 times. Where? What should be our first section?
Sir, ये spot के ऊपर.
Okay, let's call this as our x1.
Yes, sir.
And then the second section will be
UDL से
here.
पहले, sir. UDL पे.
Let's call this x2. Third section, let's call this as x3. Fourth section after UDL,
Yes,
that
sir.
will be our x4 and the fifth one over here. So if you remember, we would take the section at the point where some load is acting. For example, if there is a point load, then we should have taken 2 sections on this beam. Since there is no external load over on this beam or on this member, so 1 section will satisfy our condition. So for this frame, what will be this reaction? what will be this particular reaction? Now this is a determinate beam. Try it again. So what will be this AY reaction?
सर ये यूडीएल कितने रेंज पे लग रहा है
10 meters.
So 200
AY. And what will be this BY?
200.
What will be this BX? How much?
So 0 है.
Yes. So this is x1. So what will be the moment equation for section 1? Daniel, this is the third time I'm asking you.
0.
सर मैं बहुत कंफ्यूज हूँ इसमें अभी तो सर कॉन्सेप्ट्स मेरे वीक है
Why you are confused? These are the things that we have already discussed in the previous course.
यस सर सर आई नीड टू रिवाइज दिस आज की क्लास सर मुझे स्पेयर कर दें नेक्स्ट क्लास में इंशाल्लाह आई विल हैव ऑल द नॉलेज इंशाल्लाह
So I can mark you absent in today's class. Is it fine?
सर मैं क्लास लेक्चर ले तो रहा हूँ लेकिन मुझे चीजें कंफ्यूज कर रही हैं और मसला यही है
What is the confusion? I'm asking that, right? Give me the equation of movement. There is no rocket science behind this one.
x1
For example, if I give you this beam, there is this load of 200. This distance is x1. What will be the equation of movement?
200 into x1
200 into x1. Are you sure?
तो सर मोमेंट तो परपेंडिकुलर एक्ट करता है 200 तो बिल्कुल उसकी लाइन में ही लग रहा है
Yes, exactly. So what will be the equation?
सर
Can I say that?
जीरो हो
It is zero.
जाएगी
So it is 0.
यस
So for section 1, our equation of moment is 0. What about section 2? Again, we have to transfer this load. This will be our frame. This will be 200. This will be 200 over here. Again 200. And here we have 200. Over here 40 kilonewton per meter. That is 10 meter length. So what will be the equation of moment for section 2, which is somewhere over here?
सर ये जो डिस्टेंस है सर 200 into x2
200 into x2. For section 3,
yes sir
let's take the section 3 from here to any random distance. So what will be the equation of moment?
सर 400 into x3
What?
सर 400 into x3
Okay, leave it. Someone else? Daniel is saying that it should be 400 into x3. Do we need to consider some other force as well?
सर वो जो ट्रांसफर हो रही है उसका डिस्टेंस 0 है, तो वो उसकी वजह से तो फिर उसको काउंट मैंने इसलिए नहीं किया। जो
This 200,
3 square.
this distance is 5. This is x3.
अच्छा
Actually, there are two ways to take this. I showed, for example, you could have taken this x3 from this right hand directly to this point, to any random point from the center. But I intentionally showed you this x3 from this center because in some of the problem you will find that they would take the reference at this point. In x4, we would take this distance x4 just so that you should be aware. Even if you take x3 from this particular point, or you will take this as reference, you need to consider the forces or all the forces that are acting to the left of this point. So if I write the equation for this section 3, I will write the equation as 200 into x3 plus 5, and the
yes, sir.
second force is this 40 that is acting in the opposite direction. So my equation will be minus 40 into x3. So it will convert this into point load, and the moment at this section will be half of this one. For example, it will be something like 40. This distance is x3. So if I convert it into point load, it will be 40 x3 that will be acting at the center, x3 by 2, x3 by 2. But I am calculating the moment at this particular point, so that will be 40 x3 into x3 by 2, right? And the another way to write the equation for this section would be that I will take the distance x3 from the start. So in that case, the equation will be 200 into x3, and the second one is this moment. So that will be minus 40 into x3 minus 5, x3 minus 5 by 2. So that will be the equation of moment if I take the reference, the starting point of this particular number. So any confusion about these two equations? So you can use the both equations, but there is one difference, and you need to figure out what is that difference while taking the limits of this section. So any confusion about this one?
सर ये 5 वाली समझ नहीं लगी कि ये 5 कैसे आया,
Which
x3 plus 5.
5 is the distance, this distance from this point to this point in the original question. For example, if I ask you that this is the beam 200, this distance is x3, you need to find out the moment at this point. This distance is 5 meters. What will be the moment at this point?
सही होगा सर, थैंक यू.
So this is how you can write the equation. So for now, we will consider our reference as this particular point. Okay. And the fourth section, we will take it from the start just so that you can have an idea of both the method. So what will be the equation for section 4? Usman,
जी सर. Yes.
what will be the equation for section 4?
So 200
200
x3 plus 5.
section 4. This is the
So
distance x4. Why do we need to consider
x4
x3?
x4 dot 200 x4
And
um, uh, 40x 400. So
400
um, 5 plus x.
How much?
5.
Let me plot this over here. 200. This is 40. This distance is 5. This distance is 10. So if I convert this into point load, that will be 40. This will be acting at a distance of 10. And our x4 is somewhere over here. So now give me the equation. That will be 400. So what will be this factor?
So x4 minus
How much?
x4 minus 10.
Yes, this distance is x4 minus 10. So, any confusion about this one? So try to be real quick about this one, because this is not the main thing that you need to be doing, because these are the things that you already know. So now we have, there is a fifth section as well. So the fifth section is over here. There is a load of 200. This is x5. So what will be the moment equation for section 5?
0.
So again, that will be
0.
0. So now we have 5 equation of movement, but still we need to have, or we do need to find the small m. So now we will apply a load of 1 or a unit load at this particular point and write down the equations for other sections. So we have this beam, this frame. We will apply a unit load in the direction of displacement. We have this reaction, this reaction, this reaction, and we will remove all other loads. So what will be this reaction? Zia, what will be this AY?
सर AY 0 होगा.
Then say it. What will be BY?
0 होगा सर.
What will be this one?
1 px.
So what will be the moment equation for section 1?
सर x1.
That will be x1. For section 2, that is over here.
सर ये 0 होगा सर.
0. Anyone else?
x2 sir.
How come? Have you resolved this frame?
तो
This
0
is
ही
our.
होगा.
0 ही होगा.
So what will be the reaction at this particular point? This will be transferred to this point, 1. What will be the moment at this point? How many reactions do we have in case of frames, or at any particular joints? How many internal forces we have? We have 3 forces, this force, and the third one is movement, right? So the horizontal force is same, 1. The vertical force would be 0 because there is no vertical reaction over here. What will be movement at this point? Hasna, what will be this movement?
सर ये जो M2 का बता रहे हैं ना,
No, I am just talking about this frame as a whole. This is member A. What will be the moment at this particular joint?
Sir, it's
Excuse me, sir.
x1.
How much?
x1. So
X1.
x1.
You know the distance 5. You know the load, unit load 1. Will this
So
moment
it's
be 5?
5. Yeah, 5.
Why it's so complicated? What will be the moment now? We have to transfer this moment. So what will be the moment at this joint? At this end?
Sir, 5.
Excuse me, sir.
Yes. Yes.
सर मैं पूछना सर कि आपने AY और BY को 0 क्यों लिया है?
AY and B. What should be the values? What do you think it should be?
अच्छा हाँ, अब यूनिट वाले को करें तो फिर तो वो 0 ही होगा ना सर?
Yes.
अच्छा हाँ ठीक हो, थैंक यू.
सर एक्सक्यूज मी सर.
Yes.
सर ये दोनों ऑपोजिट नहीं है. ए वाई इक्वल्स टू माइनस बी वाई, तो हम लोग मोमेंट निकाल के बी वाई नहीं फाइंड कर सकते और फिर ए वाई उसका ऑपोजिट हो जाएगा.
I leave it up to you. You should try finding it. Even if you do that, you will get both of them as 0. Okay.
Okay, sir.
So you should try it. So
ठीक है.
what will be the moment at this end of the joint?
फाइव होगा सर.
Again, it will be 5, but the direction will be opposite. This one is clockwise, that would be counterclockwise. And what will be the moment at this end of the joint? There is no external force acting. So again, it will be 5, but the direction will be opposite. This one is counterclockwise, this will be clockwise. And this will be transferred to this end, and that will be again 5, and the direction is opposite. So what will be movement at section? This is section 2. So what will be movement M2?
-5.
-5. What will be movement M3? M3 is somewhere over here. What will be the movement?
So 5.
How much? Again -5. -5 because we are taking this as negative. What about M4?
-5.
Let's take it as -5 because again it is the same thing. And what about M5?
सर
Yes.
सर इसमें जो x4 है ये हम कहाँ से कहाँ तक लेते हैं? x4 जो सेक्शन हमने लिया हुआ है ये सब समझने में कहाँ
This
से?
is our member X4. The reference of X4 is this one from the start to after 10 meters. This is 5 meters, this is 10 meters. So any point from this point to this point, that is our section X4. So the limits of X4, what will be the limits of X4? Can you tell me?
It's sir 5 to
5.
0 to 5 हो जाएगा. अच्छा no
Zero.
sir 0 to 15 हो जाएगा.
0 to 15, do you think so? Section 4 is valid for this particular region.
Sir 0
so
to
limit
20 हो जाएगा. 0 to 20. अच्छा ये वाला 0 to 5 कहते हैं.
Can I say that it is 15 to 20? Because 0 to 20 means that it is valid for this 0 as well, or for 2 meter as well. So if I substitute 2 meter, then this equation or equation for M4 is not valid because it is valid only for this particular region, right?
Yes, sir.
So for X4 is 15 to 20.
तो सर ये लेफ्ट साइड से इसमें
Yeah,
यूडीएल जाएगा और उससे थोड़ा सा आगे वाले पोर्शन के लिए
no, UDL is not included in this one. It is for this particular region, this one, after UDL. Okay, so the limit should be 15 to 20. Why I am taking? Because we are taking this as a reference point. It has nothing to do with this UDL or any other thing.
तो फिर सर हम इसको राइट साइड से क्यों नहीं ले रहे?
You can take it. I'm not saying that you can't take it from right side. You can do it. It's up to you. You can take the limit from this end, reference as this right man. Then what will be the limits?
Okay, sir.
What will be the limits in that case?
उस केस में सर 0 to 5 हो जाएगा.
That will be 0 to 5. Yes. So it's up to you.
सही.
So what will be the equation for small m5?
इस केस में सर
this is a x5, this is 1. So what will be the moment?
So -5.
This is x5. -5. How come?
तो मोमेंट को फिर दूसरे जब उसमें सेगमेंट में लेके जाएंगे.
There are two ways. Even if you go from this path, okay, let's do that also. This was 1, this was 1, 1, 1. So when you will be solving this, you will see that you will get a 0 moment at this point. It will cancel out somewhere over here. Sorry, this moment was 1.
वर्टिकल फोर्स नहीं है वन. आपने राइट बीम राइट जो सेगमेंट है फ्रेम का उसमें वर्टिकल फोर्स लगाया है वन. तो हॉरिजॉन्टल नहीं है.
Yes, it is horizontal. It isn't 0. There are two ways to do it. Either you start from this one and transfer all the forces to this particular joint, or the other way is, or the easiest way is, you should start from the right end. It's up to you. So by starting from right end, you are getting the equation as x5. But why I am doing from the right side? Because in this initial structure, I did it from this end. For example, that is 200 into, in that case it was 0. Since I was doing it from right end, so I have to follow the same convention. In this case, if I had come from this left end, or if I have resolved all these forces, then I should have started from the left end in this case as well. So whatever convention you follow in your primary structure, you should follow the same one in this section where you have applied this virtual load, right?
सर M1 और M5 दोनों -x1 और -x5 नहीं होंगे?
-x, okay, let's take it as minus, because both of these are producing negative. So now we need to figure out delta A. So what will be that? Again, we know the equation is 0 to L m over EI into dx. So the first, we have 5 equations that we need to substitute in this one. So for the first equation, m1, I think it's better to make a or we can do it for the next question anyway. So for the first one, what are the limits for the first section? That is x1 section. What will be the limits?
So 0 to 5.
0 to 5, and the equation of moment is over here capital M1 is 0, small m1 is minus x1 over EI into dx, right? The second one is section x2. What will be the limits for section x2?
0 to 5.
Again it is 0 to 5. The moment is 200 into x2 and the small m is minus 5. So that will be minus 5 over EI into dx. What about third section? What will be the limits?
So 5 to 10.
The limits are 5 to 10. (200) into x3, where is the equation? 200 into, oh, we should have simplified it a bit. 200 x3 plus 1000 minus 40 x3, or that will be 20 now. 20 x3 square. So the equation will be 1000 plus 200 into x3 minus 20 x3 square over EI, and again the equation was minus 5, that will be dx3, this is dx2, dx1. So what will be the limits for this one?
The 0 to 20.
0 to
20.
20. Why 20?
सर 15 नहीं होगी 0 to 15.
Why 0 to 15? This was our member on which this load is acting. The reference point was this end of the UDL, right? And this particular equation for M3 is valid for this section. So can I say that the limits for this one is 0 to 10?
Right.
Is there any confusion about this one? It could have been 0 to 15, but in that case, you should have taken this x3 from the starting point to anywhere in between this UDL, just like we did in the case of x4. In x4, we took this one as starting point, but even in that case, that won't be 0. So we'll see for x4. But for now, is this clear that why I have taken this as 0 to 10? Because this particular x3 is valid from this distance, that is our 0 now, and to this point, that is 10. Right? So if there is any confusion about this one, we can ask.
Sir,
Yes?
सर ये 5 to 15 क्यों नहीं ले रहे हैं? तो 5 से start हो रहा है.
What is 5? This distance?
X3 की है सर बात कर रहा हूँ.
Yeah, you are talking about. But what is our reference point, or what is our starting point? Starting point is this one. That starting point would be always 0. For example, in this case, when we are taking x4, or let's say in x3. Oh, wait a minute, just write the equation for x4 and then you will know why it is not starting from. So what will be our equation for x4? The moments are, I'm directly writing the equation, that will be 200 into x4 minus 400 into x4 minus 10 minus 5 over EI into dx4. So what will be the limits for this section, this x4?
The 0 to 5.
Why 0 to 5?
So UDL के बाद
x4,
meters.
x4 is starting from this point. So from the point, whatever is our reference will be always 0. So 0 is this point for x4, right? But x4 is valid only for this particular section from 15 to 20. For example, if I substitute x4 as 0 or x4 as, let's say, 2 meter, that will be this distance from here to here. That will be 2 meter, right? So, but this x4 is not valid for this 2 meter. This x4 is valid for this particular distance. Does it make sense?
Yes.
Okay, I'm giving you one exercise. For now, we are taking x3 starting from this particular end. Now, you can again do a small exercise and write the equation for x4 from this particular end. From here, you should assume that this is x4 starting from this end. Now, in this case, the limit will be 0 to 5. And when even if you write the equation of movement for this section, you will get the same answer. So it is up to you that whichever procedure you feel convenient, you can adopt that. I am doing both the method just so that you are aware, because in some of the examples from the book you will see that they are taking this as a reference point, and in some of the example they are taking this as a reference point. So whichever method you adopt, it's fine, it's up to you. Okay, so you can do it, or you must do it, that you should take this as x4 starting from here. Then in that case your limits will be 0 to 5, but your equation for M4 will also change slightly in this case when you take the reference as this point. So you should do it just like we did it for the X3 case. Or the other way around is that you can start, or you can take X3 also from this starting point and write the equation for X3. But in this case, your limits of X3 will be again from this point 5 to 10, but your equation of movement will change, but the final answer for the deflection will remain the same. So if you are still confused, you can adopt the same approach for both x3 and x4. So you will get the same answer, don't worry. Okay, so if for now I am giving you one thing, that is, if you start from this if you take this point as a reference, then you should take the limit separately for everyone. For example, for x4 we took this point as the reference, so our limits will be this 15 to 20. But for x3 we are taking directly from the start of the load, so this will be our starting point of the section. So our limits will be 0 to 10, because we have written we write our equation of moment according to this one. So you can try both methods. So now coming back to section 5, what will be the limits for section 5?
Zero to 5.
That is a simple 0 to 5, and over here we have x5 dx5. So now give me the answers of these integrals. This will be 0. What will be this one? You can use your calculators.
12,500.
So this one is 12,000. How much? This, right?
12,500 over EI.
With a negative sign. What will be this one?
Negative 66.7 exponent 3 over EI.
66.7
exponent 3.
Are you sure about this one?
Yes, sir. Yeah.
0 to 10. Can you please check this one again?
Sir, 53333.
Hold on. Can you check this answer again? Is it 66.67?
Yes, sir. Exponent 3, sir.
Exponent 3. You should tell me that. And what is this third one? This one. Minus 12 into 500 over EI. So that is delta A. So what is final delta A?
So minus 91,666.67.
666.67. So this is our delta A. So we have calculated one factor in this equation, that is 0 is equal to minus 91,666 EI plus we still need to find out FAA into AX. So can anyone tell me that how can we get FAA? जिया कैसे कैलकुलेट करेंगे?
सर यूनिट लोड ट्राई करेंगे जो यूडीएल है उसकी जगह.
किसकी जगह? This is our structure, right? We don't have a UDL actually. This is our structure जिसमें हमने FAA find करनी है. So how will we get that?
सर जहाँ पे डिफ्लेक्शन होगी अगर वहाँ यूनिट लोड लगा के वहाँ डिफ्लेक्शन फाइंड करना तो कुछ इस तरह से.
This is the unit load.
यहाँ पे
So we apply the unit load and apply the virtual work method or find out this deflection, that will be FAA, right?
Yes.
So in that case, what will be our equation? That will be again 0 to L, capital M, small m, EI, dx, right? So what is this M? Can anyone tell me that how will we calculate or how will we write the equation of this capital M for this particular case?
स्मॉल एम होगा.
What?
स्मॉल एम स्क्वायर ओवर ईआई.
So okay, we will go by the procedure. Now the first step is, now this is our initial structure in which the unit load is acting. So we have to write the equation. But in the virtual case method, in the second step, you apply the same unit load in the direction of deflection, and you will write the equation of small m. So this is capital M, this is small m. But in this case, both of these capital M and small m will have the same equation, because in both of the cases we have same unit load that is acting at this particular point. So can I say that FAA is 0 to L m square over EI dx. Now we already have equation of small m for this frame. We wrote it over here. These are the equation for small m for this particular frame. We just need to take the square of these equations, and we will get this factor FAA. So is there any confusion about this one? So we can again write the equations. That will be for section 1. The limits would remain the same as we used in the previous cases, because we wrote the equation considering these limits. So for section 1, EI into x1 square dx1. For section 2, our equation was 0 to 5 square over EI into dx plus 0 to 10, 5 square over EI into dx plus 15 to 20, 5 square over EI into dx plus 0 to 5 into 5 square. So what will be FAA?
सर पहला वाला 41.66 है.
That is 41.66 over EI. These two will be same, so just add them.
So x1 और x5 माइनस में नहीं लिए थे हमने?
But you can take it as minus. The square root will be positive, obviously. And by the way, this is also x5. These two are not same. This is x5. Everything is negative, but when you take the square, it will be positive. So what will be this one?
125.
125 over, yeah.
Next वाला 250 है.
250 over here.
सर अगला 125 ही है. और फिर 41.66.
So what will be the final answer? So FAA would be, if you add them, you will get 582.66 or 583 point something. So this is your FA. Now you have got both the factors. If I substitute them back into the compatibility equation, I will get minus 91,666.7 over EI plus AX into 583.33 over EI. So this will go on to this side and will be 0. So what will be AX now?
Sir, 157.
157 kilonewton. So now if I write this in our original structure, so we had a hinge support at this end, a hinge support at this end, 40 kilonewton load at this end, 10 meters, that is 5 meters, 5 meters. This is also 5 meters and 5 meters. Now we have this direction. We assume this direction in the start and we have got the positive sign. So that means that this direction was correct. So this is 157 kilonewton. This is 40 kilonewton. And these three reactions now we need to find out. So what will be AY, BY and BX? So what will be AY?
So ये वही initially वाला होगा 200 kilonewton.
How come? What will be B1?
सर y पे तो फोर्स सिर्फ उसके पाए हो रही है यूडीएल वाली तो फिर तो 200 नहीं होना चाहिए ए वाई और बी वाई को
और यहाँ के आपने वैल्यूज जो है इसमें फीड की और चूंकि आपके पास आपने
And what will be BX?
157 kilonewton.
Again 157 kilonewton. Actually in this question it was a symmetrical structure. So in this question it is by, let's say, our luck that we got this as 200 kilonewton, but this is not the case that in every case these reaction will be the same as the ones in the previous one, because in this one it is symmetrical section and we could have got these reaction directly by just looking at this frame, because this load is acting at the center, all the lengths are same, all the distances are same, so that's why these two reactions are just the half of this UDL. But you will see in the next question that these are not the same every time, so you should solve them by applying the equation of equilibrium or equation of motion. So the last step is to plot the shear force and bending moment diagram, and I expect you to do this by yourself. So I leave it up to you to plot the shear force and bending moment diagram. So any question about this particular example?
यस सर, ये हम जब फ्रेम सॉल्व कर रहे थे ना, तो उसमें हम ऐसे कर सकते हैं कि मतलब इनिशियली हम लोगों ने x1 वाला सेक्शन सॉल्व किया, फिर हम लोग जो है x सॉल्व कर लें, और मतलब हम लोग x4 जो है, जिस तरह हमने x2 लिया है, हम x4 को मतलब इस तरह से लें, जैसे x4 को हम लोग जो उसका रेफरेंस पॉइंट है वो हम लोग राइट साइड से ही रखें। हम लोग एक साइड से स्टार्ट करें, पहले लेफ्ट से स्टार्ट करें, फिर राइट से स्टार्ट करें, और फिर मतलब हम लोग मिड तक उससे मतलब करते करते मिड तक आए, जैसे x3 को लास्ट में सॉल्व करें।
x3 को लास्ट में सॉल्व करें, आई डिडंट गेट दिस वन।
सर जैसे ये मिड सेक्शन नहीं है यूडीएल वाला, मतलब अगर हम
दिस वन वाज x1, आप कह रही हैं कि ये x2 है। नेक्स्ट क्या क्वेश्चन है आपका?
हाँ, और ये मिड वाला सेक्शन भी x3 ही है, लेकिन मतलब x4 जो है वो एक्सट्रीम राइट से स्टार्ट हो जाए।
राइट से, या यू कैन डू इट, इट्स अप टू यू। फिर आपको यहाँ से रिजॉल्व करना होगा और फिर उसके अकॉर्डिंग आप देख लें, और फिर उसी के अकॉर्डिंग आपकी वो लिमिट्स आएंगी 0 to 5 इन दैट केस। सो दिस इज अप टू यू। मैंने आपको दोनों तरीके बता दिए हैं, अब आपके लिए कौन सा कन्वीनियंट है वो आप सेलेक्ट करें। दिस इज एक्चुअली द सिमिलर एग्जांपल। ये दरमियान में तो जो भी सारा प्रोसीजर किया है ये वही वर्चुअल वर्क मेथड वाला प्रोसीजर हमने बेसिकली किया या फ्रेम एनालिसिस का। सो ओनली डिफरेंस वाज राइटिंग दिस कंपैटिबिलिटी इक्वेशन। सो बाकी सब कुछ यू ऑलरेडी are aware of these things. So any other questions? So let's start another example. If there is. Now we have this frame in which there are two fixed supports. We have different moment of inertia for three different members. For this member we have I, this left member we have 2I, this right member, this top member has 3I. We need to analyze this frame as well and plot the shear force and bending moment diagram. This is the frame. We have 36 kilonewton. Over here, 3 meters, 3 meters. This is 96 kilonewton, 3 meters, 6 meters, and 7.5 meters. This have I, 2I, 3I. This is A, B, C, and D. So what is the degree of indeterminacy of this frame?
Three.
So we have 6 unknown, 3 equations. So the degree of indeterminacy is 3. So we need to take 3 reactions as redundant and write the compatibility equation accordingly and solve this. So let's start this one. So we will, you can take this A support as redundant or this D support as redundant. It's up to you. I did this question by taking this D support as redundant. So if I take this one as redundant, I will get, so the my primary structure would be, this will remain as it is, and over here I will remove this fixed support as a whole. All these loads will be acting as they are acting in the actual structure. This is 96, 3, 6, and just assume that these lengths are in meter, or just I will not be writing the units, just understand that these are in meters and these loads are in kilonewton. So this is our primary structure in which we will have 3 deflections, and about the direction of deflections, just take this deflection in the same direction as you will be taking in the redundant structure. So we will have this as our horizontal deflection. This is D point, so I will call this as delta DH. DH means that the deflection at D point, or the horizontal deflection at D point. This is our vertical deflection. I will call this as DV. That means the vertical deflection at point D. And the third one is obviously our rotation. So that will be this theta D, or just call it as theta D. That means the rotation of this particular joint D. Then we will again have our first redundant structure, because in this case we have removed 3 reactions, so we have to apply all these 3 reactions at this particular joint D separately and then write the equation of compatibility equation. So in the first case we will apply the horizontal reaction, that let's call this as HD. This will be our horizontal, reaction, and due to this one there will be a horizontal deflection. Let's call this as delta dash h h. That means that the horizontal deflection at point D due to the horizontal load. That's why I'm using this term HH. Then we have a vertical deflection as well. So I will call this as a VH. That means the vertical deflection at joint D due to the horizontal load. And the third one is rotation. Rotation I will just represent it with the arrow sign or movement sign just to keep things simple. So I will call this as theta h, or the rotation due to the horizontal load acting at this point. Right? The second frame would be the one in which I would apply vertical deflection or vertical reaction at this point. Let's call this as VD. Now due to this vertical load, again there will be three deflection. I will call this as delta VH, delta VH. That means vertical deflection. Sorry, it should be delta HV. Horizontal deflection at this point due to vertical load. Then we have this one. We can call this as VH. That means the vertical deflection due to, sorry, it should be VV. That means the vertical deflection due to vertical load. And the third one will be this movement, and we can call this as theta V. The rotation due to the vertical load VD, which we have applied on this particular one. You can name them or you can use any sign notation as long as you understand what you are doing. It's fine. And in the third case, we will apply this particular movement, which we can call as theta D. That theta D, we have already used that term. We can call this as MD, or movement at point D. Okay, so due to this movement, again we will have three deflections or three kind of deflections and rotations. One is this one and this one. So this we can call as delta H theta. That means the horizontal deflection due to the applied movement or applied rotation. This we can call as delta V theta. That is the vertical deflection, and this one we will call as theta theta. That is the rotation at point D due to the rotation or due to the moment MD, which we have applied at this particular point. So these are our three structures, and quickly we can write the compatibility equation, and in the next class we will be solving this one. So the compatibility equation for this particular frame, first we will write the equation for the horizontal deflection. For example, in this initial frame at point D, you can see there is no horizontal deflection, so that will be 0. In this frame, you can see that there is one horizontal deflection, that is delta DH. In this second frame, you have this horizontal deflection, that is delta HH. In the third one, again you have this horizontal deflection, that is delta HV. And in the last one, you have this deflection, that is delta h theta, right? Then we will write for the vertical displacement. In the initial frame, again it is 0. In this primary structure, we have delta dv. In this structure, we have this delta vh. In this third structure, we have delta vv. And in this fourth structure, we have delta v theta. And then we will write for the movement or rotation. In the initial one, again it is 0. In this structure, we have this theta d in the primary structure. Then we have this theta h, or I can call this as theta dh. Let's call this one. Replace this with theta dh, this as theta dv. So in this structure, we have theta dv. And in the last one, we have theta theta. dh means that the rotation at point D due to the horizontal load. This is the rotation at point D due to the vertical load, and this is the rotation at point D due to the movement that we have applied. So this is the compatibility equation, and if I simplify this one, I will get from the first equation 0 is equal to delta dh. Then this I can replace it with fhh into hd due to the, since it is due to the horizontal load. Then fhv into vd plus the last one as alpha, because it is the rotation, so we should have angular flexibility with this one. That will be alpha h theta into md. The second equation will be delta dv plus this factor will be fvh into hd, because it is due to the horizontal load that is acting at that particular point or at point D. This one is due to the vertical load, so it will be vertical flexibility or Vd, and this one is due to the rotation, so it will have again angular flexibility V theta into Md. And the last one is,
class.
Yeah, we are just concluding. Theta d. This one is due to the horizontal load, so that will be alpha dh into hd, plus this one is due to the vertical load, that will be alpha dv into vd, and the last one is due to the rotation or movement, so that will be alpha theta theta into md. So these are the three compatibility equations. Now in these equations, you have how many unknowns? First, we need to find these three reactions, right? These are the basics unknown. So we have these three unknowns that we need to find out by solving these three equations. But to find these three unknowns, we need to have these 3, 6, 9, and 12 deflections. Then we can find these three unknowns. Now, your task is to write down the equations for the, or just think about that how can we figure out these 12 deflections by method of virtual wall. Just think about it, and in the next class we will be solving this frame. So if there is any question about this compatibility equations, you can ask me. So is there any question? So if there is no question, then this is it.